We're back with another episode of programming an NES game here today. It's Thursday the 8th, and if you remember last time we left off when we were coding, we had finished refactoring the V-blank code out of our finished refactoring the game loop code out of our V-blank so that it was separated and being handled differently and externally from the V-blank code. And then we had added an additional button press so that we could spawn another type of entity besides just the bullet. We added this flyby type. And then the flyby type we implemented, it just was essentially creating another bullet. But the bullet was scaling sort of down the screen, and so that looked like this. So we have the ability to fire those enemy flyby things, which are just coming out wherever the exposition of the ship is, and then we can fire actual bullets from the ship. So hopefully today we're going to do some collision detection between the bullets and the enemies, and I also want to refactor the loop that we're using here, or the code we're using here, to add the entities to the entity memory, because I don't know, it was just bothering me that we had these kind of completely discrete parts of code that were doing mostly the same thing. I mean, there were parts where it was different, so I think we can potentially, I think there are parts where we can keep this the same and then just differentiate depending on the type that's being handled. We'll see. It seems like we should be able to do that. Before I get started, though, there was a comment that was brought to my attention by Kevin from Kahan Games. If you don't know Kahan Games, it's Kevin makes awesome homebrew NES games. He also is one of the hosts of the Assembly Line podcast. If you're interested in NES programming, you should definitely check it out. It's a great podcast, and they talk about the homebrew scene, new games that are coming out, old homebrew games that have come out, anything that's kind of new and interesting in the NES homebrew scene. So definitely check that out. But he had watched the intro video and pointed out that NMI and V-blank are not the same. And so if we go back to here, if you remember, I've been talking about, if you have your TV, you have your V-blank period where it's the electron gun presumably sweeping up on an old CRT, or the monitor is waiting to refresh the screen, and during that period, that's when we're computing what needs to be drawn for the next frame, so that it happens smoothly as we sweep down the screen. And I had mentioned that that was called NMI. He correctly pointed out that NMI is actually slightly different than the V-blank. The NMI, the non-maskable interrupt, is what's actually triggered during the V-blank period. So it's a really subtle distinction, but basically the NMI is a generic thing. It's an interrupt that can occur, and in the case of the NES, it's, as far as I'm aware, the only non-maskable interrupt. So it's an interrupt that can't be turned off, or let me rephrase that. It's an interrupt that couldn't be stopped from happening if it's supposed to occur. That's what the non-maskable part means. So the interrupt itself is different than the V-blank. The V-blank is, in and of itself, what causes the NMI to be triggered, but it is not an NMI. So hopefully that kind of clears up that distinction. It is, again, pretty subtle, but wanted to bring that up because there is a difference, and you know, there are other systems that use non-maskable interrupts that have nothing to do with V-blank. So Didn't want to confuse those two things. Also, you know, there are interrupts that you can have on the NES that are related to other things and are generated by the cartridge mappers and stuff like that, but that's not something we're going to deal with at the moment because we don't need it necessarily. So, yep, just wanted to kind of clear that part up and give the podcast a shout out since it's pretty awesome. Really enjoy listening to it. And in fact, that's the reason why I started doing this, is because I started listening to the podcast and then started reading into what's involved in doing NES programming and decided I was going to do this live stream. So let's get started with the code. So when we left off with the enemy, it was just using a bullet sprite. I wanted to add a different kind of sprite, so I just created this also 8x8 little square block. And the reason I wanted to do that was just to distinguish it so it looked a little different. So this tool, YYCHR, is a simple tool for just directly editing the char ROM for your NES game. You can see I'm using this shooter char file, and that's being loaded right here at the end in the char segment, so that when the assembler creates the output file, it's just putting that data directly into the cartridge or the ROM that's assembled. All right, so now that I've created that additional sprite, I want to actually make that entity use that. So let's go to where the flyby, okay, so the flyby sprite gets updated here. That's going to increment the tile, so instead of being tile 1, it's moved over to tile 2, right? Because the tiles go across this way. So that's tile 2. And if I leave the PAL alone, you can see that we've, if I can hit the right keys, you can see that we have changed it. So now when I hit the B button, it's going down the screen. Now the only thing is that the palette that it's using is not exactly what I wanted. I wanted to use the same palette that we're using for the ship. And if we go back, well, actually we can do it right there. If we look at the player type sprite, the palette that it's using is just palette 1 versus palette 2, which is being used by the bullet. So I'm going to change this palette to palette 1. And again, this is the 4 byte set of information that you set for each 8x8 sprite. Or if you're doing 8x16 sprites, it's the same kind of idea, but in this case we're doing the 8x8, and each of the 4 bytes has meaning, right? So it's the X, Y position, the tile, the palette, plus some additional information, and the X position. So by doing that change, if I rebuild it and reload this and hit the B button, all right, so there we go. We've got the new sprite moving, but one thing that I don't really like about it is I don't like the way that the speed matches. Right away, it kind of looks weird that the speed matches the background. So we can handle this a couple of ways. In the game loop, we're updating the flyby so that it moves at a certain speed. So let's go to the game loop, and where are we checking our entities? So that's where we're adding them. This is where we're processing them. So here's the flyby. I'm adding 2. I mean, I guess I could add 1 and see what that looks like, but I feel like that's still maybe not going to be what I'm looking for. I want it to be maybe a little more floaty. I want it to kind of move a little bit more slowly across the screen so that well, that's not too bad. I mean, that's definitely more along the lines of what I was looking for. But I think I want to use this as an opportunity to add to the entity type some additional storage. And so what I want to do is go to the entity type. I want to add an additional byte that's essentially specific for the entity. We're going to call it data. And in here I'm going to say entity specific information. So for now, I think that'll be sufficient. And what I want to do here is when I'm updating the flyby, I think what I want to do is, instead of just adding directly to the Y position, what I want to do is I want to load A with the data value. So essentially what I'm going to do is I'm going to add this whole data value, or I've added this data byte to the entity. And what I want to do is I want to increment a counter inside there before I increment the Y position. So essentially every frame I'm going to be incrementing data by 1, and then once I hit a value that I feel works well, I'll then increment the Y position in the entity so that we can slow it down even further, because right now we're essentially adding 1 pixel per frame, and what I'm looking to do is sub-pixel movement, essentially, right? I mean, we can't set a floating point value on the Y because this is a whole integer and it doesn't support floating point, but we can definitely do this method where we're essentially kind of cheating and saying, you know, data will represent some smaller chunk of information, and then or some smaller interval, and then once it reaches the maximum value we want, it will then increment. So if you picture it, it's almost like we're implementing our own floating point, right? I mean, not really, but it's the same kind of concept in that you have your Y value, and then you have this counter. I should do it a little bit different. You have your Y value, and then you have the counter. And depending on what value you use, let's say the counter goes from 0 to 100. Well, then basically what you're saying is that each time you're counting here, you're going up 1/100th of a pixel, right? I mean, again, you're not really doing that because you're not incrementing this Y, and the NES doesn't support sub-pixel resolution. But you could think about it that way, that it's going to give you that smaller, sort of smoother motion. So let's do that just to see. I mean, that's going to probably be super slow, but that's okay. So I always forget if it helps if I spell Chrome correctly. The increment is there's X increment memory. So there's increment memory, but there's not increment A. So what I want to do is I want to increment X. Yes, I want to increment data. First, I'm going to load it into A. I'm going to compare it with 100. Well, it's 100 hex. That's not what I wanted. That's too big. 100 in decimal is 64 in hex. And then branch if not equal, we're going to skip the addition of the 1 pixel. We're going to branch to, we'll call this process flyby skip increment. You know, and I know that's a long label, and it doesn't affect anything in terms of the way that the code is assembled at the end of the day, because it's still just an address. But I don't know, I tend to like more verbose names for things because then it's more clear. I mean, you don't want to get too crazy, but you know, and start writing sentences. But I prefer that it's more verbose than less, and have it just say, you know, skip or something like that. So, and I've certainly done that before. I'm not saying I always do it, but it's just one of those things where, it's probably better to be more verbose in this case. So, especially with assembly, because there's just so many instructions to do anything beyond basic operations, it will get confusing real quick. So I forgot the index there. So load it, compare it to 64. If it's not equal, then go to process flyby skip increment. Otherwise, I want to increment that. So what I first want to do is I want to reset the counter in data. Load A with that and store it into entities plus entity data X, and then I'm going to just increment this because I'm trying to do just a single increment, so I don't have to do the load and store. It's just going to increment the Y position there. I do need to do the load here because I want to see what the position is and make sure that I'm not hitting the bottom. And then we can leave that alone. And then once we hit that, okay, so that all looks good. If I assemble that, I can close the calculator for now. And I broke something. All right, well, part of it might be that curious. So there were no flybys to process, so what did I break? It's an adventure every time you make a change. So I'm curious what actually broke because of this change. Why? Okay, I have two versions of FCEUX running. That's probably not great either. Okay, it's kind of interesting how it keeps adding. All right, let's find the game loop here. And let's see, those are the controller calls. So I want to go to the beginning, and so I'm looking for it to where it's loading A with 0 and 0, 2 to do the sprite mem set. 0 and 0, 2. Okay, so set a breakpoint here, and then we'll reset the game, see where we are in terms of memory and everything, and how it all looks. So right away that looks wrong. That looks wrong because it looks like the sprite memory overwrote the rest of the memory. So that's strange. That's the dog. You can ignore him. Okay, so I broke it by adding that. It's right. I know you're not going to know what data is. That's fine. 423. Oh, let me just comment all of that out for a second. All right, so now that that's there, let's restart again. Where's the debugger? That looks more like what I expected to see. Although, yeah, so that looks more like what I expected to see now with the beginnings set properly. So, all right, so just by adding that byte, something got broken. Okay. Let's see what it is. Am I... let's do just 2 entities and see how that looks. Debugger, hex editor, reopen it, and run. No, see, that still looks wrong. So that... So that's initializing the player, and then it's increment. Oh, see, this is what happens when you try to be clever and you do something like this where you increment by 3 x increments separately rather than using the entity size. So let's talk about this for a second. So I had done this because if you look at I and X, you can see that there are 1 byte instructions that require 2 machine cycles. So it was 3 bytes and 6 cycles to do this versus incrementing X. So in order to increment X, let's see, to add to X, I should say. If I wanted to add to X, basically the only way you can do it is you are transferring X to A, right? So, I mean, basically I was trying to be clever and do all of this sort of, do the kind of unroll this, these operations into just smaller, faster operations. So the transfer X to A is also 1 byte and 2 cycles, so that's the same. But then when you want to add, you want to clear your carry. Now, presumably I could probably figure out what the state of the carry should be at that point. But that's 1 byte and 2 machine cycles. So far we're kind of neck and neck. And then you want to do an add with carry. And this is 2 bytes and 2 cycles. So so that's again neck and neck because, well, it's 1 more byte, but it is the same number of cycles. So you have an extra byte there, which, you know, presumably we want to be as small as possible when we do this, but then you also have to transfer A back into X because you've added the value of the size to A, and then you transfer it over back to X, and that is where you save a little bit because instead of having to do this and eat up an additional, so it's 2 additional bytes and 2 additional machine cycles to do it this way. But on the flip side, I caused this bug. And the interesting thing is, you know, if I think about this right now, this is kind of a stupid place to do optimization, right? Because this is just the initialization, and frankly, I mean, if it takes a little bit longer to do the initialization, who cares, right? I mean, I'm not talking about seconds here. I'm talking about a few extra cycles per entity. So maybe it would have been smarter to do just the add by entity size. Now the question actually becomes, what am I doing elsewhere? If I go to, because we have the clear entity process here. See, and this is maybe a place where it would have been more appropriate to do what I'm doing because this is going to be happening in the game loop over and over again. Of course, this would have broken anyway. So this is the problem with trying to do premature optimization, is you don't really know where your code is going, and you end up breaking things. You end up breaking things that you probably didn't need to break, because depending on your game, it may not need that optimization. I mean, obviously, again, you don't want to be you don't want to be sitting and optimizing for hours necessarily if your loops are running too slow. But at the same point, why optimize when you don't need to? So for the sake of not breaking this again, what I'm going to do is I'm going to do the longhand way, and I'm going to put a note just for myself for later, possible optimization. So transfer X to A, clear the carry, add with carry through, size of entity, transfer A to X, and that's that. And then what I want to do here is to do possible optimization using NX versus longhand, right? Just want to make a note while I'm in it, and remember that this is even a possibility. Put this into here, and I can always come back to it later. It may not even be relevant later, because we may change how this all works, but it doesn't hurt to put this here. All right, so now that should be fixed. And let's go to the debugger. There's a hex editor debugger. Let's run until we get to the loop. We're going to be close to it anyway. Let me find where the loop begins, and let's see. So it was at F4, which is here. So where did it move to now that we changed the instructions? So it's now over here, right? What happened? Did I get us into an infinite loop now? Seems to be that way. Transfer X to A, clear carry, add carry 4, transfer A to X, compare X with 8. Let's take a look at this. Why did this get stuck? Let's add the breakpoint here instead, so that we're going to catch it the first time around. Let's delete that and run and reset the. Okay. So, oh, well, yeah. If you set it to, no, well, that doesn't matter because it's going to transfer X. So why is X 3? X is, oh yeah, well, because you got to initialize the new byte too. So that was no, it's because that should really be size of entity, not just hard-coded 3. Okay. Right, so that was off because the entity used to be 3 bytes, and then I changed it to 4 bytes before I had started using size of, and so that broke. Okay. All right, cool. So maybe now it'll work. Let's see. Well, it looks better possibly. So run. Let's just step over. It should, yeah, it looks like it's going to break out of there now. We run till we get to the game loop. Okay. Remove that breakpoint. And okay, cool. So that's better. So now, all right, so now you can see this thing is moving super slow. And if we go to the game memory in the hex editor, what you'll see is that, let's see, where is our sprite memory, or entity memory beginning? Okay, so the entity memory begins here. This is the player's X and Y. I can tell because when I move, they're changing. So if I move up and down, the second byte changes left and right. The first byte changes, right? And then that's the entity type, and that's the additional data byte, which for the player doesn't mean anything right now. This is the flyby that we added. So this is its X, this is its Y. And this is the data byte that we added that's doing the counting. So you can see it's counting up, and then when it hits the point that that we predetermined in the code, it's incrementing the Y. But obviously, like I said, that's super slow. One nice thing about that is that you can actually see the blinking palette because of the palette change we're doing, which is kind of neat. Makes it look interesting. Definitely way too slow. So we had changed the number of entities that were in the system, so it can't even add a bullet. Let's change that back. Let's make that, let's go back to 10 entities here. Where was that? Max entities, 10. Assembled, okay, so let's run that. There are bullets, there's the flyby. It's moving super slow. We can't actually shoot it yet and destroy it because it doesn't, there's no collision detection. All right, so that's all well and good, I guess. We probably want to change that so that it's moving a little bit faster, just because that's super slow. So instead of 64, let's just say, let's just say 5. Let's see how that looks. This is one of those things where I think we're just going to know based on when we look at it how it feels. That's okay. It's still too slow, I think. Let's say 3. Not the assembly. Okay, yeah, that's a little bit more like what I was thinking. I wanted to move a little bit more slow, and then, you know, maybe at some point we'll add a little more logic to it so that it might, you know, try and follow the player ship. Is it better to make it even just half speed? Is that, I wonder if that's even more than enough. Let's see. Yeah, that's good. That's along the lines of what I was thinking it should look like. You can see I'm running out of bullets, or I can't fire more bullets because there are too many entities in memory. So if I were to, let's see, we have 10, so I could do these entities and then I can't fire any bullets, right? Not really practical for a shoot 'em up game where we probably want more. I mean, it's not going to be like, you know, a modern game or something where you have hundreds of bullets flying around. If you've ever played Everyday Shooter or something like that, I mean, that's I don't think that's possible on the NES with all the hardware and memory limitations. But we can definitely up this. Let's say 20. See. Okay, so that's too big. Why is that too big? 452 total entities. Oh, because it's beyond. So what? Okay, so we are limited to 64. No. Size of it, 4 bytes. If we set 4 times. Really? What are you doing, keyboard? 4 times 20. That's 80 bytes. So total entities is 20, unless that's not. Oh, is that in hex and not in decimal? That would make more sense. Yeah, that would be 32. Yeah, okay, that's why. 20 in hex is 14, right? If that's what the problem is. Looks like it. Okay. So that built, and now I can add a bunch more of these guys and still have the ability to add some bullets. Now, part of what we might even run into with this number of entities is we might run into the problem, sort of the classic Nintendo problem of too many sprites per scan line. So the NES has built into it hardware where it can fit up to 8 sprites per scan line. So what does that actually mean? So if we go back to that picture of, you know, the screen drawing back in the day, you had, you know, the electron ray gun scanning across the screen. It was drawing one line of the game. And let's say you have 3 sprites here. It's drawing one strip from each of those sprites as it scans across. And there's a limitation that you can't have more than 8 of those. And so if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So you have that 9th one there. That one doesn't actually get drawn. And so you won't see it on screen. And so what we're all familiar with from playing games on the NES is that concept of the game flickering. And that flicker is actually something that's programmed into the game. So that was something that I had no idea was the way that it was done. So it's kind of amazing. You end up having to write code into your game to detect that you've got more sprites per scan line than are supported, and then what you do is you shuffle your sprites around so that it creates that flicker effect, so at least you can see them even if it's imperfect on the screen. And I'm sure we'll have to get to that with the number of things we're going to want to have on screen at one time. But for now, let's just be aware that that is potentially going to be an issue where we're going to think we see, you know, we want to be aware of it so that when we get the collision detection working, we don't feel like the ship is getting destroyed incorrectly because we can't see the thing that it's colliding with. Because in memory, if our entities are starting here, where that scrolling was occurring as I add these flybys, I can add more than we can see on the screen, I believe. So interestingly, no, well, can't in this case, or it doesn't seem to be the case. That let's see if we can make it happen, just for fun. No, I can't seem to make it. I wonder if that's just an artifact of the emulator, or if that's legitimately. I wonder. Let's take a look and see. because some emulators have the ability to essentially make it as if the NES had additional sprites, which isn't always it doesn't always work. Some games rely on certain and I don't even know the details necessarily. I just know that they rely on certain features of the quirks of the fact that there are only 8 sprites per scan line, and it will break if you increase that number. And systems like the Analog NT Mini and the Retro USB AVS have that support in it. So for some games, it reduces the amount of flickering, which is nice. Well, that's interesting. Why is... Well, it should definitely be using hardware acceleration. Doesn't look like it's... Oh, okay. So here's the option. The allow more than 8 sprites per scan line. It's not doing that. Let me restart this and see if that setting made any difference in the performance of the game. It seems about the same. Anyway, so I guess because they're staggered, I'm not getting that effect exactly that I want. But anyway, all right. So I wasted enough time on that. All right, so that's looking good. So let's talk about collision detection and what that looks like. I'm going to step away from NES programming here for a second to show you an algorithm that allows you to do collision detection on very simple, well, it's going to be square shapes, just because it's a pretty basic algorithm, and it deals with basically what it's looking at, or not what it's looking at, the way that it works is you have two squares, and each square has a particular size. And if you look at the x and the y of the center of these squares and the width, what it says is, okay, there's a certain distance that these centers can be from each other, right? And if that distance is less than the sum of the widths of these squares, then they collide. So why is that? Because if you look at this here, right, let's say this is 8 and this is 8, right? They're 8 by 8, and this is 8 by 8. Let's say that this is at the origin. So this is 4, 4, and just for the sake of simplifying this a little bit, let's say that this is here. Again, you have your origin, and it does the same thing for the y. It looks at the difference of the y positions, and based on the size of the squares determines whether or not it's even possible that they would collide, right? So if you so this is 10, 0, let's say. So if you take the difference of the center positions here, this would be 14, 4. So if you say 14, 4, right, the difference is for the x, and it's times 2, right, because you're factoring in the whole width of not just the half the width from the center. If that's less than in this case, 8 plus 8, right, which is 16. And what you'll see, and this is the absolute value. If you're doing it the math way, right, it's the absolute value. You get 10 times 2 is 20. 20 is less than 16, which isn't true. And if you, as you bring this closer, you'll see that this distance closes in, and eventually, if this were to overlap, let's say it's at 7, 0, right? Well, so then the math works out. Is there a way to do a selection in here that I can just clear just that instead of having to erase this whole thing? I can increase the size. Well, it's better. So if you do the math, you get 7 is so it's 14. Right. Let's write this up here. So x2 minus x1 absolute times 2 has to be less than width 1 plus width 2, right? So in this case, you get 14 is less than 16, and in the case of no, I did that wrong because it's the center position that you're looking at. So in the case of this, it's 7 plus, that's 11 and 4. I mean, it still works. It's just I did it wrong. So this is 4. So it's 11 minus 4, which is also 7 coincidentally. So it's still 14 is less than 16. So you can see that for that x, it actually satisfies that part of the check. And then you do the same thing for the y. You say y2 minus y1 times 2. It's less than width 1 plus width 2. And you do the same check, right? You see, so it's 4 minus 4 is 0 times 2 is 0 is less than 16. So in this case, it collides as we would expect it to. If we were to do a similar comparison where the x is still 7, but the y is, let's say, 10, the center point is now 11 and 14. And if we do the math here, we see 11 minus 4 is 7, which is 14. Because 7 times 2 is 14 is less than 16, right? Because the width is 8 and 8. But where it doesn't satisfy, because these both have to be true, is you have 14 minus 4, right, is 10, and times 2 is 20, is not less than 16. Okay? So this algorithm is pretty straightforward. It works really nicely. Debating whether or not I want to demonstrate it here. I think I will, just for the sake of showing it, and then we're going to talk about why it's not going to work in its current format for what we're trying to do. And you'll have to excuse me. I'm going to use JavaScript to do it just because it's going to be the most expedient way to do this, I think. So what I'll do is open this up, and we'll just create a very basic HTML file. Okay, so just get all the usual crap out of the way. All right, so that's that. We're going to create a canvas. We're going to give it an ID of canvas. We're going to give it a width of 800, a height of 600, and then we're going to actually do our scripting. So I want to have two rectangles. Do I want to do it this way? I don't care. That's fine. Nah. Yeah, that's fine. I don't care. That'll be the simplest way to kind of make it obvious what we're doing here. So we'll have an X, which is going to be 0, 0 to start. We're going to have Y, which is 0. We're going to have the X center position, which is going to be 4. The center Y position is going to be 4. And put the width into here, I think. And you know, by width, because it's a square, we only need to store the width in one direction. There are algorithms that'll do it in multiple directions. If you look up Minkowski collision detection, I believe that that has more general purpose collision. But for what we're doing, you know, this is applicable for square bounding boxes, which is probably what we would be doing anyway, more than likely. But let's go with this to start off with, and it's not going to work anyway for a reason I'll get to in a second, but it'll be interesting for us to look at why it works or how it works, and then why it doesn't work for what we're trying to do. And what's cool is this will work for two squares of any size. They don't have to be the same size. All right, so the canvas is document get element by ID is canvas. Our context from the canvas is right. So that's our context. And then let's start off with doing we'll just set a so this is what's going to actually do the drawing. We're going to set up an interval to do it. We can start a little bit slower just so that we don't go nuts with the browser if I make a mistake, which I'm bound to do. Let's just get those drawn first. So context fill style is equal to, let's say we just want black. Okay, and then fill rectangle rect x, rect y, rect width, rect height. Oh well, rect width, it's the same thing. And then we'll do the same thing with rect 2. So if I haven't screwed that up, it should draw two rectangles. And there they are. They're really small. So let's make that bigger. All right. So there you go. We have their two rectangles. And now I want to be able to move one of them. So let's just do this. Key down is on key down. We'll check key down. On key up is check key up. And then let's add some key states here. Key up is false. Key down is false. Key left is false. And key right is false. So I'm just, keeping track of which arrow keys are pressed on the keyboard here, just for the sake of simplicity. And we'll do the updating of the rectangles not in the key presses themselves because it's much slower, but we'll do it in the actual we'll do it in that refresh that's getting called. All right, so check key up event with e.keys arrow up. So this is actually checking the release state. So key up is equal to false, else if theta key is equal to arrow down, key down is equal to false. Left, right, key left, key right, and then we want to do the same thing for when the key is pressed down, and just reverse what we're checking, or reverse what it does, so that makes it true. And then in the loop, we want to say, okay, if the key up is true, then rect x plus, we're just going to add 1, and center x as well, and then down. Well, that's stupid. If it's up, I want to actually, well, wasn't really thinking about what I was doing here. I was just kind of putting the logic down and being dumb. So key down is going to move it down the screen, so it's going to increment the y value. Key up is going to decrement the y value and the center y value. Key left is going to decrement the x value, and right is going to increment it. Okay, let's see how broken that is. It's seriously broken. Okay, so what did I do? Else if, yeah, that's not in this language. Okay. Where'd my browser go? Good. Okay. That's cool that you're scrolling, Chrome. I don't really want you to, but... Oh. Okay, cool. So that's actually working partially. I gotta clear the canvas every time. 255, 0. Context fill rect 00 800 by 600. Well, I can do canvas width, canvas height. Let's just say we're going to do that for the sake of if we change the canvas size for some reason. What did I break now? Context fill rect. Oh, I spelled it wrong. Spelling matters. All right. Great. So that's all working now. I can move that one rectangle. Not very exciting though, because nothing happens when they collide. So what I want to do is I want to apply this formula. So if you remember, it's the delta x times 2. Where is my drawing? It's the delta x times 2, and we're checking it against the sum of the widths. And it's the delta y, the absolute value of the delta y. I want to check that both of those conditions are true. So what we're going to do is we're going to say if it's true, we're going to set the fill style to green. Otherwise, we can set it to black. All right. So, well, you know, let's set it to red. Let's make it more dramatic. All right, so if we do this, it's math absolute rect x minus rect y. Nope, that's not it. It's rect 2x times 2. Let's do a bit shift. That has to be less than rect width plus rect 2 width. And come on. Math absolute rect y minus rect 2 y times 2. Same thing there. We could probably pre-compute that. Don't really need to, I don't think. So that is doing the okay, so yeah, it's the absolute value of the x delta times 2 compared to the rectangular width of both of them together. Same thing with the y. And if both of those conditions are true, it will draw in green. Otherwise, it will draw in red. So if we go back to the browser and refresh, it's in red. And you can see as soon as they get close to each other, it crashes. Awesome. What did I do wrong? I typed fill style wrong. Great. There you go. So they turn green, and you can see it's the scrolling. Scrolling aside, you can see that when they touch, they turn green, and when they don't touch, they're red. Pretty straightforward. And so you might say, okay, well, let's implement that on the 6502. And the problem is a couple of things. Well, the first is there is no absolute value function. And that in and of itself isn't such a big deal. We could do our own value of our own version of an absolute value, because the 6502 does detect when numbers of operations result in a negative number. So let's say you do a 5 minus a 10, you should get -5. Now, technically, well, this gets into a whole bunch of stuff. But so technically, you would get -5, and if you looked at the value in the emulator, well, let's do that. Let's look at the value in the emulator, and we'll talk about why it does what it's doing. So we can close our little collision example here and go back to Sublime Text. We don't need that HTML anymore. So let's start off here. So let's do this here, right? So if I load A with a value of 5, and then I set the carry and I subtract a value of 10, right, which is in hex, should get -5, right? So let's do the old trick of putting some no-ops in here so I can find it more quickly when we go to the emulator. Here it is, and let's go to the debugger and go to 8000, and there are no ops. Okay, so let's set a breakpoint here so we can look at what's happening when we hit that point. Okay, so right now A has no value, so I'm going to load the 5 into it. I'm going to set the carry, which set the carry flag there. I'm going to subtract 10, and you can see that the value changes to FB, and that does not stand for Facebook. It stands for the number. We get it in hex. The decimal number 251. And so, if you're not familiar with binary, you should read up on 2's complement and how negative numbers are represented in signed versus unsigned values. But basically the idea is that a signed value, or let's start with the unsigned, right? So a byte unsigned will have a range of 0 to 255, which is 0 to hex FF. If you do an unsigned, if you do a signed, the range is, and I'm always off by 1 when I do this. It's negative 127 to 128. Is that right? Signed byte minus 128. Yes. Okay. So, all right, I got it right. 128 to 127, and the reason for that is because of this concept of 2's complement. So there's a way that you can sort of very cleverly represent negative numbers in binary, even though there's no sign flag. So you could be saying, okay, well, why not just have a bit where if it's set, then the number is negative. So in hex, sorry, in binary, the number 5 is 101, and let's say these bits are all part of this byte, and it's 8-bit. You know, let's say, okay, set this to 1 if it's negative. The problem is then if you want to do something like I want to add 5 to -5, well, how do you do this? I mean, you have to start doing some convoluted logic to make this work, right? But instead, there's a way that you can really, interestingly, you can make this work where you just add those two numbers and the result is 0. And you do that using 2's complement. And the way you derive the 2's complement value of the number that you're looking for is if you're looking for the number 5, for example, and you want -5, the way you do it is you flip the bits, so all the zeros become 1s and all the 1s become 0s. And then you add 1 to that. Okay. So now we have this value that normally in a unsigned byte, let's see, what was that? What would that represent? Because I don't know off the top of my head. 1 1 1 4 1 0 1 1. Wait a minute, I wasn't in binary mode. 2 3 4 1 0 1 1. So in right. So this is exactly the case we're doing. I didn't realize I was even doing that until just now. So it's 251 unsigned, right? But if I take this value, so we have the 5, this is our -5. Let me redraw those 1s. And if we were to add them together, you should get the value 0, and you do. So 1 and 1 is 0, carry the 1, so 1 and 1 is 0, carry the 1, 1 and 1 is 0, you carry the 1, 1 and 1 is 0, you carry the 1, and so on and so forth. You get zeros all the way until you get that carry at the end, which drops off and sets the carry flag. But you get the value of 0. And that's how 2's complement works. And it's really cool because now you have a way of efficiently taking two numbers that are signed, adding them together, and getting the appropriate value. Now the problem is that because you're representing the numbers this way, it effectively changes the range of possible numbers that you can represent from 0 to 255 to this -128 to 127 because of the way the bits get set, right? At some point, you're going to get a series of bits that represents the 2's complement value of a positive number, so you've effectively flipped to negative. So why does that matter? Well, it matters because when we're doing our algorithm here for the collision detection, right, we have to do the delta of the x and the y and take the absolute value. So that in and of itself isn't too hard, because if the two values were 5 and 10, like we said, right, if we get -5, the nice thing is that the 6502 will have set the N flag, the negative flag. And so what we can do is we can put something in our code here that says, okay, so BPL is checking the N flag, the negative flag, and checking to see if it's set. Basically, it's saying if it's a plus value, if it's a positive value versus a negative value, then you're going to branch. There's another one called BMI, which is branch minus, which does the opposite. So we can say branch plus, no flip, or skip. So skip apps. Okay, we don't have to do anything because it's already positive, and that's what we're looking for when we do the absolute value, right? But if it's negative, we have to invert the 2's complement value back to a positive, and it's the same thing we already talked about. So the value in A is going to have that value that we got from the subtraction. So we're going to do the EOR, right, the exclusive OR with FF, right? And last time we talked about how the exclusive OR works. So that's just going to flip all of the bits that are already set to 0, and the bits that are not set are going to get set to 1. So that's easy enough. And then we clear the carry and add 1. That's 10 hex. We add 1, and then we're done. So if we put the label to skip the absolute here, or maybe we'll call it skip TC, skip 2's complement, right? If we go back to the assembler, or to the emulator, I should say, and come on, and reload the game, and reset it. Debugger, where's my, okay. So here's our code again. So I'm going to load 5 into A. I'm going to set the carry. I'm going to subtract 10. I'm going to get FB, which is our 251, as a positive integer, but it's really -5 in 2's complement. But the negative flag is set. So when we check if positive is set for the branch, it's going to not take the branch because it's a negative. So we branch, we use the exclusive OR to invert the bits in A. And in doing that, we get the value 4, right? Because by flipping the value of 251, so 251 in binary looks like that. It's 111111 1011. By adding 1, we're changing this 1 to 0. Sorry. By flipping the bits, we're going to 0, 0, 0, 0, 0, 1, 0, 0, 0. Wait a minute. What am I doing wrong? I've done something wrong here. I'm distracted by the dog howling upstairs. So this becomes 0, 0, 0, 0, 0, 1, 0, 0. Right. And then we add 1. Eraser. And then we add 1. It goes from 4, right? Well, if this is 1, 2, 4. So this is 4. We add the 1, and we have the value 5. So we've converted it from negative to positive, which is what we wanted to do with the absolute value. So no problem, right? We can do this now to our heart's content. But there is a problem, and the problem is, what do you do in a situation where you have something on the screen? Let's say the X value is really far to the right and the Y value is really far to the left. Well, now the problem is, because the width of the screen is 256 pixels, but we can only represent -128 to 127, if we get outside of that range of values for the delta, now we can't choose, now we don't appropriately know whether or not it's negative, and we need to flip the bits and add 1 to convert it to positive, right? Because the resolution of the values representable is not sufficient. If we could do something where it was -255 to 255, well, then we'd have the ability to do that absolute value correctly without worrying about running out of resolution, because at most we know that we're going to do 0 minus 255 in the case of the x coordinate and get a -255 and have to do the inversion and the add 1 to get the positive value from the 2's complement value. So unfortunately, while this is a really clever algorithm for us, based on what I'm seeing, I don't see this working for us, and we're going to have to choose a different approach. I think I'm going to stop for now, and we will actually implement the collision in the next episode. I think we've covered a lot here, and hopefully this was interesting to everybody. If you want to see more, I'll be streaming again Monday of next week at 9 p.m. Eastern. You can reach me on Twitter at Claravis. You can leave comments on Twitch while we're doing this, and you can chat with me while I'm doing the stream. And I'm also going to post the video to YouTube. So if you want to watch the recording, you can watch it after the fact. And feel free to comment and like the video. Reach out to me and let me know if you have any suggestions or anything that you'd like me to cover besides what I'm covering here. But once we get past the collision, now we can start implementing screens for the game, and we'll actually start to be able to really build a shooter for real, start implementing some larger enemies, and probably I'm thinking I want to do some sort of background scrolling to make it a little more interesting than just the background that's there, the star background, because that's okay, but it's not. I mean, probably want to do something a little more interesting that kind of teaches how we're gonna load in background data and handle background collision. So anyway, thanks for watching, and see you next time.